Welcome on my presentation on the economic and environmental benefits of smart farming, case studies on variable rate applications. My name is Abdul Mouazen. I am the group leader of Precision Scoring group at the Department of Environment. I would like to acknowledge my sponsors that sponsored the main research results of this presentation, that are FWO and ICT Agri-Food. The content of my presentation consists of presenting the context of this presentation. Then I will talk about current variable rate practices and what is the future possibility for variable rate practices using multi-sensor and data fusion approach. And then we'll discuss some case studies on the use of variable rate technologies for seeding, fertilization, and manure applications. The majority of agriculture field have significant variability, and the degree of spatial variability depends on the field and the agriculture practices. But the way is done today to manage to apply farming inputs in a homogeneous way is not ideal, because this will have not only economic underperformance, but also environmental consequences, in addition to low crop yield. And that's why this within field spatial variability has to be managed differently, and this is done by the 5R principles that include using the right products in the right time, right rate, right place, and right technology. I will start with giving the example of nitrogen fertilization, how it's done today in a variable way. You know, there are two different scenarios that being adopted in practice commercially. The first one is the example of FIARA sensor, where they have used proximal crop sensors to measure nitrogen requirement of the crop, and then these based on that they apply variable rate nitrogen fertilization. Other solution is based also on satellite imagery for the measurement of crop canopy characteristics to determine nitrogen recommendation rate. On the x-axis, which is the other commercial solution of nitrogen fertilization, is based on EMI scanning, followed by the collection of one sample per hectare or per field, or per management zones, and these samples are sent to the laboratory for determining the mineral nitrogen, and based on that, recommendation for variable rate nitrogen fertilization is established. But both solutions are limited because they either depends on one sample per hectare or per management zone, or in the case of crop data, they ignore soil data completely. And we see that the future solution is to have large, high resolution data on not only soil but crop and other auxiliary data affecting yield. And these are really fused and integrated in advanced decision support system to calculate the nitrogen recommendation rate. This is all because yet today we are unable to measure mineral nitrogen using proximal soil sensing. That's why the multi-sensor and data fusion will be very much appropriate to manage nitrogen in the soil site specifically. But as you see, when we implement variable rate technologies or precision agriculture technologies, we have to tackle even a field as agricultural systems, which means that we should be able to measure with high sampling resolution the key parameters affecting crop yield. That includes, for instance, soil properties or soil fertility attributes, crop characteristics that could be measured with satellite imagery or with UAVs or whatever, in addition to weather conditions, topography, and these together with yield data, these are all put together in an advanced multi-sensor data fusion approach based on machine learning or deep learning in order to produce recommendations for variable rate application. And in order to collect all these data, you should have some key sensor technologies that are able, and some advanced decision support tools and advanced modeling tools in order to be able to not only to derive the optimal recommendations, but also for implementing variable rate applications in a precise way. For that, I give you an example of what we have here in Ghent University in our faculty under my group. We have an online multi-sensor platform that consists of a tine to cut the soil, and behind it there is a lens holder in which there are two lenses, and these two lenses are connected to a visible and near-infrared spectrophotometer via two fibers, one fiber to illuminate light and the other fibers to collect back the diffuse reflected by light into the spectrophotometer. This sensor can be put on a frame, and the frame can be put on the back of a tractor and can be driven within 3 to 5 kilometers per hour speed. And at the end, what we can get is a soil map for key soil properties, mainly organic carbon, clay content, moisture content, with high accuracy, and also we can measure secondary soil properties like pH, phosphorus, magnesium, calcium, cation exchange capacity with a lower degree of accuracy because they don't have a direct spectral response in NIR spectroscopy. But also that multi-sensor data fusion approach has a load cell and a depth sensor, which enable, together with moisture sensors, to even measure and map bulk density, which is the indicator of soil compaction. And here is a map comparing the manually measured bulk density map with the online measured bulk density map. You see high similarity between the compaction layers and loose layers between the two maps. But also we have developed a portable system that is also equipped with NIR spectrophotometer, and there is an optical fibers being put in within the shaft of the penetrometer, and then there is a sapphire window, and that collect diffuse reflected light. And in the same way as we have seen for the online system, we can predict some key soil parameters like moisture content, organic matter content, and even bulk density based on data fusion approach. And in addition to that, we have even connected the sensor to frequency domain reflectometry sensor technologies in order to measure volumetric moisture content. And by the combination of both the online sensor and the portable system, we are able to map soil properties in 3D. Coming back now to site-specific nitrogen fertilization, this is an example of the results we have obtained in the last few years, where we have fused the data from the visible near-infrared sensor, including 8 layers of soil properties, together with crop yield data and NDVI data measured by satellite imagery. And and in addition to that, we used apparent electrical conductivity, and based on clustering, we have derived the fertility zone maps. Each of these zone maps were assigned a class of fertility, and based on its correlation with yield that we have measured with combine harvester. Then we have designed a strip experiment where we have 3 types of treatments. We have a uniform rate treatments. We have variable rate treatment 1, which is the green one. That is the traditional way of application, as we have seen in the first slide. And then the advanced multi-sensor data fusion variable rate application, which is variable rate 2. And we overlaid this strip experiment over the fertility zone maps in order to run and compare between the 3 different treatments with sufficient replicates. Results showed, and that is the field was in the UK, that extra profit, net profit to the farmer of about 50 sterling, UK sterling, can be obtained compared to a uniform rate, while only 25 sterling can be net profit to the farmer compared to the traditional variable rate application. And when we added to N fertilization phosphorus and lime, then the profit goes up to about 72.8 sterling per hectare. We have even run the variable rate cost benefit analysis in other fields in Germany and Turkey, and we see that profitability could range from 24 euros per hectare up to 355 euros per hectare, depending on if you use N only, then it can go up to 98 euros per hectare, like the case in Germany, while if you add NPK, this can go up to 355 euros per hectare. But what we also noticed that not only profitability can increase, but also the use of fertilizer can be reduced. And this is, as you see here, we have seen that for innovative variable rate approach compared to uniform rate approach in 2014, compared to that in 2015. So when we discuss further the environmental consequences of using this one online sensor, one online soil sensor that can cover 6,800 hectares per year, then the environmental saving could go up to 142,000 sterling per hectares. Because, you know, when we put N fertilizers, when we manufacture N fertilizer, when we use extra N fertilizers, the way that we do that homogeneously, then that will lead to a contamination of our groundwaters and surface waters with different types of agrochemicals, and this has to be cleaned. Somebody has to clean this, and who will clean those? Policy makers has to have programs to clean those natural resources, and cleaning them will be very costly. And you see, the one sensor can save up to 142,000 euros per hectare if they cover almost 6,800 hectares per year. Another example, we have fused the data on soil with data on crop measured by hyperspectral camera and satellite data on NDVI. The hyperspectral camera enabled for the first time the online measurement of yellow rust, and then the field was divided into 2 classes. Each classes either have low yellow rust or high yellow rust, which each of those will receive different rates of fungicide, and based on that, the variable rate application, we have calculated a profit of up to 35 pounds per hectare net profit of using variable rate fungicide application for yellow rust management site specifically. If we took the same approach for fusarium detection, then a saving, if we use those fusarium maps for dividing the yield into different categories, like healthy for human consumption, partially contaminated for livestock consumption, or maybe highly contaminated for energy production, then, and that's what we call selective harvest. So 3 different categories of yield, then the profit can go up to 48 sterlings per hectare. Recently, we have also did some work on multi-sensor data fusion for site-specific manure application. Again, we have developed a management zone or fertility zone maps, and here we compared variable rate application using King's approach compared to Robin Hood. When I say King's, meaning that I feed the rich, I apply more where I have more fertility, and in the Robin Hoods, I apply more in the poor fertility zones, and we try to compare which one of those will be profitable compared to the uniform rate. Our results showed that variable rate technologies, both the King's and Robin Hoods, can increase yield of up to 1.2 to 2.3%, and increase profit by 1.9 to 2.1%, while reduction in N and P can be only obtained by the Rubin-Hood's approach, where the use of N can be reduced by 4.1% and P can be reduced by 7.1%, while unfortunately the King's approach has used more N of 1.8 and more P of 3.1. Although King's approach provided almost 40 euros net profit per hectare compared to the Rubin-Hood's that provided about 36 euros per hectare, we believe that the Rubin-Hood's should be applied because it reduces the use of N and P, which means that from economic point of view, both provide the same, almost similar output, but the Rubin-Hood approach will reduce the environmental consequences due to the reduction of the use of N and P. We were surprised when applied this multi-sensor data fusion approach for site-specific potato seedings, and in this case we only compared the King's approach compared to the uniform rate approach based on management zone maps developed with VisionIR sensor on soil properties, EMI sensors, and satellite imagery, where we have seen our results for an increase in yield of up to 2.62% and reduction in costs of 0.6%, and that profitability increased by 10.32%. It's surprising to see that the net profit per hectare can go up to 476 euros, and we have seen in one field also, so like 500 euros profit. So the profit scale here is 300 to 500 euros per hectare for seed potato production, while we have seen for nitrogen fertilization, for manure, we are talking about 50 to 100 euros per hectare. So because potato is cash crop, the expected profit is very high compared to those of fertilization that we have seen in the previous slides. I'd like to conclude that we need to use advanced sensor technologies, and that is the multi-sensor data fusion has to account for all yield affecting parameters in the system. We should really consider a system approach in here, even when we deal with one field as a case of focus. We need to have a high processing capacity and maybe perform calculations in real time in the cloud. And where it's possible, we should implement the real-time control of farming input. It's clear that there is a huge potential, not only from economic, but also from environmental point of view. Thank you very much for your listening. This is my contact details if you wish to talk further about this with me.